Okay, in this video we are going to be talking about simultaneous solutions, and I've also noted next to the word simultaneous solutions, I've also called it functions that intersect, because that's how I like to think of it a lot of the time. I like to picture what's going on, and the way I see it is as intersecting linear functions. Now, you can have simultaneous solutions for not just linear functions, but we are only going to be looking at linear functions in this video. How I'm going to go through explaining it is consider the graph below illustrating the growth of two different species of trees. Now, I haven't called them any particular name, these types of trees. All I've done is called them tree A and tree B. And what these two lines are representing are the growths, or is the growth of two particular trees. And you'll see that the growth of each tree is different. This one appears to be growing a bit faster than this one. But you'll also note time zero down here, the time at which they were first measured. This tree, tree A, was a lot taller than tree B. Tree A was 8 meters, tree B appears to be 3 meters. And that would be suggested by the C value being the y-intercept of their functions. So, what we have illustrated above are two linear functions on the same xy axis. It is evident that at some time, the time being after a number of years, the functions will intersect. Now, what that is saying is it is clear that from these lines they're getting closer and closer and closer, and at some point up here somewhere they're going to intersect. But you'll note it's off the graph. Now, one relatively quick way you could solve this is extend the graph and both functions and actually visually find the point at which they intersect, which would work. But if we're given two functions that more or less look relatively parallel but are not, they might not intersect for a long way up in that direction, in which case it's not realistic to extend the x and y axis and extend the functions to try and figure out why they intersect, because you might need loads and loads of paper to do it. So there's a better way to go about it, and this is what we call simultaneous solutions. So if I move back down to where we were, the intersection of these two functions will occur when they are equal to each other. Now, what that is suggesting is that if we let these two equations equal each other, we'll be able to find the intersection point. Now, if that doesn't make sense, that's okay. It will become clear in a second, hopefully. What I've done is I've rewritten tree A and tree B with their corresponding linear functions representing their growth. I've labelled them as equation 1 and equation 2 in case I want to refer to them in the future. So how do we determine at what value on the x-axis, being the time in years, these functions will intersect? Being at what point on the x-axis here, how many years, it'll be 11, 12, 13, 14, 15, 16, we don't know, how many years will it be when these points or these two lines intersect? If y equals x plus 8 being equation number 1 for tree A, and y equals 4 on 3x plus 3 being the equation of tree B, then x plus 8 must equal 4 on 3x plus 3. If you're not sure how I've got that, hopefully you'll note that because y equals y in both of these equations, this must be the case. Now, if that doesn't make sense, I'm going to try to explain this a little bit more clearly. What we have is a y value, and it's suggesting that it equals this. But we have another y value here, and because they're both y's, they must be equal to each other. So this y is this y. They're the same thing. Okay, so this y equaling this and this y equaling this must suggest that this is equal to this, which is what I've written here and then called equation 3. So that's how I got it, and that's what this means, because y equals y in both equations. Because these things are the same, these things must be the same, which is what I've written here. If we rearrange this equation 3 and solve for x, we have essentially identified the x-axis coordinate of the intersection, being the time in years. So what we're going to do to equation 3, if you look at it, the only unknown we have is x, and you might think, oh well, I can't solve that because I got two unknowns. Well, you don't really. You've only got one unknown. The unknown is x. There just happens to be two x's in the equation. If we rearrange, we can essentially get it down to 1x and solve for it. So if we go about rearranging equation 3, the way that I started doing it, and the process in which I took, was I moved this positive 3 to the other side and made it negative 3. In the process of making it a negative 3, this drops by 3, so I took 3 from 8 to get my positive 5. So the 3's gone from the right hand side. You'll note the 3 there has disappeared. What I then did was I took this x to the right hand side and left 5 by itself. Now I took it it's a positive x on this side, sorry, so positive x. So to move it to the other side I had to make it a negative x. Then what I did was I noted, well, 4 on 3x take x is more or less 4 on 3x take 3 on 3x. So 4 on 3 take 3 on 3 will give us 1 on 3 with the x. I then got rid of this third and moved it to the other side by dividing it, or you could alternatively multiply it by 3 to get the same result, and it's going to give you 15. So that's just the process of rearranging. Therefore, the trees A and B will be the same height after 15 years. That's what this x equals 15 refers to. It's referring to the x-axis. Okay, so it's referring to the x, and it's suggesting that when this is 15, so somewhere around here when it's 15, that's where they're going to intersect up there when x is equal to 15. So we found the x-axis intercept. Excuse me. We're not finished yet. To determine the height at which the trees are equal, which is the time 15 years, so 15 years is when the trees are equal in height, all we need to do is substitute the value x equals 15 into either of the original equations, being equation 1 or 2, to solve for y, which is our height. So what I did was I substituted x equals 15 into equation 1, because of the two equations of equation 1 and 2, equation 1 is definitely more simple to solve. It's just a matter of adding two integers together, which is quite simple to do. Okay, and we get a value of 23, which means after 15 years both tree A and tree B are 23 meters tall. So what we've done there is we've used simultaneous equations or solutions to identify an intersection point or an intersecting point between two equations on the same axes.